There we go. All right, this is where we left off on Tuesday. And so I'm still basically in the same PowerPoint, but I've labeled it lecture 11 and uploaded it to the Canvas site. So some of the slides will repeat, but we'll start here. So just to review what the most transducers that produce the ultrasound look like this, in that they have a linear array of these piezoelectric crystals, which are quite thin, and voltage is applied across that crystal to make it compress and expand. And that voltage is applied up in the megahertz range to make a vibration that's, somewhere in the 1 to 5 megahertz. It can go up to 20 megahertz actually, if you want. The crystal itself, the design of the crystal, the thickness of the crystal will cause it to resonate at different frequencies. So you can carve it down smaller and thicker to make that crystal resonate at higher and lower frequencies. And one mode of imaging is to create a set of vibrations from these crystals, simultaneously phase delay them such that you get a focal point at a specific depth. Okay? And you can raster that focal point up and down if you want by changing those phases. So this is, remember, the lateral resolution is how blurry, if I have a little sphere in my sample, how blurry, what does that sphere look like in this direction? In this direction is the axial resolution, so away from the transducer. Side to side on the transducer is lateral, and then slice thickness. And we talked about the natural slice thickness of the transducer defined by its shape, and also cutting this into multiple rows of individual transducers and phasing those as well. So the primary, let's put this down here, mode of acquiring echoes from interfaces in the body is we generate a short burst of ultrasound, and this burst is like microseconds long, right? It's very, very short, few oscillations at the say 2 megahertz frequency in a window. That burst then travels through the medium, and if it goes across a boundary in which the acoustic impedance is different, it causes a reflection. And we saw in the last lecture that reflection comes back at, it can be sort of 1% of the amplitude of the original transmitted wave. Since there's two interfaces here, this pulse will cause a reflection when it passes this point, and it will cause a reflection when it passes this point. Those two reflected waves are coming back at the fundamental frequency, right? So let's call it 1 megahertz. So these oscillations here are 1 megahertz. So I have a 1 megahertz signal coming here and here. And if the two interfaces are far enough apart in terms of the size of this pulse width, right, then you will get two independent signals detected. So when they come back to the transducer, we'll flip it into listening mode, right? And the compression of the crystal by these pulses, right, will cause a voltage, and we'll measure that voltage. So the signal that will come back will still be at the fundamental frequency of this. That's say 1 megahertz or 2 megahertz, whatever it is, right? So we tune this thing to look for that signal. In terms of spatial resolution in the axial or the depth dimension, as these interfaces get closer and closer together, those two echoes will start to overlap, and there will be a distance at which you will not be able to see that they're two pulses, right? And so that is your fundamental axial spatial resolution. If you don't have enough spatial resolution, you can increase the frequency of this pulse to have the same number of oscillations, peaks and troughs. Say we go from 1 to 2 megahertz and just cut it in half. And so now I have a pulse that's half as wide, and so my axial resolution will double, and I'll be able to resolve these. Okay, so that's very simple explanation of that. We'll see that when we listen to these, packets of the fundamental frequency coming back, we really want to detect that pulse, and essentially you demodulate it so that it just looks like a DC blip, right? And so that's going to occur in electronics back here, because we know precisely what our transmit pulse was, so we can demodulate when the echo comes back. We'll see, however, that interestingly, when you put out a pulse and it's at a fundamental frequency, and so it's essentially a sine wave that has some kind of amplitude modulation on it, or an envelope. As that thing travels through the medium, in fact, it distorts somewhat from a sine wave. And we'll take a look at that. And this, in my time in medical imaging, this was one person's artifact is another person's technique. And so this causes artifacts, this distortion of the wave, but it can also be used to your advantage, this distortion. We'll take a look at that. It's called harmonic imaging. Yeah, sure.
Why don't the quets would be much lower? So as I understand,
yeah,
you have like the maximum frequency, you would probably have a maximum spatial resolution.
Right. So the quet is a very good question. Why don't you just crank? Because we can make ultrasound. This thing can vibrate at 20 or 30 megahertz. And the problem is, at that frequency, the decay of the power of the wave you're putting in is very short, right? So you won't get any depth penetration. You won't see anything beyond, say, a few centimeters if you go up to 20 megahertz. At 2 megahertz, you're going to get to 10, 15 centimeters into this sample, right? So there's a balance. So the lateral resolution, remember, and here's an example where we have these dots, and this is how you test ultrasound systems, right? You make a gel phantom, and inside the gel you put small spheres that are reflective, right? So they have a different acoustic impedance than the gel, and you image those dots, and you take a look at what the dot looks like in 3D, and that's your point spread function, basically, right? And so for this transducer, when we set the phases of the vibrations of those elements in the transducer such that we have the highest focus of the energy here, we get the best, lateral resolution at that depth. And we can move that up and down by changing the focus with this phase. And just, in a phantom, this is what it would look like. You would get a smudge of a certain width away from the focal point, right? And it's pretty. We'll see some experimental results for measuring not only the spatial resolution, but also the signal to noise as a function of depth, right? So as we were talking about on Tuesday, you can cut it into a two-dimensional array, phase in this dimension such that you get focus in the slice direction. Okay, that's a pretty simple process. I I don't know, other than the increased complexity of the electronics and the programming and the sampling and the demodulating and everything like that. Everything, you know, you've just multiplied your number of things you have to do by however many slices. Nowadays, with the miniaturization of electronics, it's not a big deal, like to make these things. Obviously, there's some dead space, you know, in the ability of your transducer to pick up all of the energy coming back to hit it, because you have to, if they're truly independent, there's got to be some space between them, right? And so that efficiency, I don't know what that is actually, but it's probably pretty high. It's probably like 90%, 95%. Excuse me. So here's a overview of what goes on and how to make these pictures. The same diagram is also in Prints and Links, basically the same labels on the boxes. And so we have some place we're controlling gains, we're controlling frequency, we're controlling, you know, depth focusing, stuff like that. It is talking to both the receiver to tell the receiver what was programmed out, right? And the machine forms the beam by doing the phase arrays and stuff like that, puts it into, I don't know what the hell a pulsar is, probably an amplifier. And then there's a switch that toggles us between receive and transmit mode. So we transmit, shut off, and listen. And then transmit, shut off, and listen. And we toggle between those two modes, right? The pulsars put out individual phased, you know, let's say it's 1 megahertz pulses to the crystals, and we sweep that across the field of view. Okay, so we have this beam we've formed, and we sweep that beam across the field of view, and we get a two-dimensional picture by doing that sweep. You can sweep it in 3D and get a three-dimensional volume, but the amount of time required goes up. And then when the echoes are all coming back, you know, when there are, we switch to receive mode. We've obviously missed a few of the very early echoes, right? Because they come back immediately. But when we're in receive mode, we pick up the echoes off all of these interfaces down here. That gets just the raw signal goes through a preamp. It's, you know, digitized, and it's then essentially demodulated back down to the a fundamental frequency. So if I'm at 1 megahertz here, I demodulate to 1 megahertz, bring it into my receiver. We do a time gain compensation, which means the late echoes that are coming from stuff down here are going to be much, much smaller than the early echoes coming from here. And so this is adjustable, actually. You can do it in real time. You look at the picture, and if everything's gone low, you can crank that gain up. And obviously, you're going to see what's there, but you may be disappointed, right? It might be pretty noisy, right? So when you crank the gain, you might just be cranking up noise, and so there's a balance there. The log compression is done so that you keep everything in a reasonable number of bits, right? Because we're talking about many orders of magnitude in dynamic range here. And if you're going to manipulate a signal, you don't want to be manipulating across this enormous dynamic range. You don't want to have 36 decimal points, right, in terms of doing this. So you crank everything down to the log scale. Oh, here's the rectification. I'm sorry, I said rectification was here. Rectification and rejection. So you would reject a potential echo coming back if it's below a certain threshold, right? You just say, look, that's equally probable that was noise versus a true interface. I'll reject that one. And so obviously features in your image, as you change that rejection threshold, when you're watching the image, you're going to have an image that's full of noise and all of this crazy stuff. And then as you turn the rejection up, the background noise will go away and your features will come into view. And, so that can be done also interactively. And then you basically put it up on the screen so somebody can look at it and adjust things here. Okay, so here's the simple, or the simplest timing diagram of how this occurs in time. And so the pulse repetition period, or PRP, is the time between the pings that you are sending out. Okay, so I'll send out one ping, and then at this time, between this ping and my next one, I listen, right, for echoes, shut it down, shut down the listening, turn on the transmit, and send out another ping, and then listen again. Okay. So as you can see, the duration here, we're talking microseconds for these little pings. And here we have about half a millisecond for the listening for all of the stuff to come back. So it's not that hard to calculate, how deep you're going to see things, because you know what the maximum time is that you're waiting for an echo to come back. And you know roughly what the speed is in the medium. If it's a liver, say it's 1500 meters per second, right? So you pretty well know how deep you're going to see stuff. And if you want to see stuff deeper, you can crank this amplitude and increase this time, right? So if we want to go deeper. But probably what's going to happen is your signals, you're going to run out of signal to noise, because the echoes from a certain depth will just be so small that they won't overcome the electronic noise and other things. Okay. So if we blow up this time period here onto this axis, so that this is now 500 microseconds along here, here you can, with the assumption that number of outflows, 1540 meters per second. Okay. These are the depths of the echoes you're seeing at that time. Okay. And so time and depth, same thing, right? Through this constant. And so it's pretty easy to make one line of your two-dimensional picture, because you know where to put these things just by measuring their time that they came back, right? So you just plot them as dots, right, on your 2D picture, or bright spots, and then sweep through that and make a two-dimensional image. The pulse repetition frequency, 1/500 microseconds. So we're basically sampling at 2 kilohertz, right? So we're sampling a line every 500 microseconds. And so our total sampling rate on that line is 2 kilohertz. So 2,000 lines per second. Any questions about that? So when we look at it in the context of an object that we're trying to image, so if we have this is a chest wall here of the patient, and we place the transducer right on the chest wall, and we'll discuss, it's not the actual piezoelectric crystal that goes onto the chest wall. You put a material, you couple the piezoelectric crystal to a softer material than piezoelectric crystal. And then that couples to the skin through a gel. So you kind of do this step down, right, in terms of stiffness or impedance, because if you just put the crystal right on it, you would have these enormous reflections right on that. So you want to optimize the amount of stuff that you're transmitting into the patient, right? So we'll see this, there's a little layer. So we send out a pulse, and we, after our demodulation and amplification and all that stuff, we get a set of pulses in time. And so time would go this way, right? And that time, as we saw in the previous one, just maps to a position in space. And so this is your fundamental signal. You have a peak. The size of the peak is proportional to how much reflection you got at that interface. So if it's a highly reflective surface, this peak will be bigger, right? If it's not as reflective, then you'll have a smaller peak. And so here, this is called the A mode. A B mode is just when you turn them into actual dots on, you make a decision and turn them into dots on your picture. And if we leave the transducer in that position and we scan at, what were we scanning at? We're scanning at 2 kilohertz, right? So you just put the transducer there, scan at 2 kilohertz and see what the hell happens, right? It's pretty cool because these surfaces, when they're moving, you can measure with tremendous temporal sampling the motion of those surfaces, right? That's why when you look at an ultrasound image of whether it's a beating heart of a fetus or, blood flow in somebody's vessel in their arm or something like that, it looks fantastic because you get this really good temporal resolution. And in this mode, this is called M mode. It's just B mode versus time. So we just make B mode images, they're 1D pictures, and you just watch them over time. And then you can answer really cool questions like, what is the fastest velocity this valve leaflet achieves, right? And then you go over here, right, and you look at your signal and you say, oh, I know that this is my anterior mitral leaflet, right, and or something like that, and I can actually measure the slope of that curve and tell you what how fast it snaps back, right? Which is, it's kind of cool. Like you can get this underlying physical measurements at super high frame rates. Right? Any
Professor,
questions?
I have a quick question.
So we can look at an example of some of these M mode pictures. So this up here, these are two-dimensional. They're single time frames from two-dimensional images obtained with a transducer that's sweeping back and forth to make the two-dimensional pictures, okay? And so you're getting these images at, I don't know, probably 30 frames a second or something, or 15. Just to orient you, this is the left ventricle, okay? As we move from left to right in this picture across here, let me put on my laser then. As I move from this one over to this, the operator is tilting the transducer such that it moves away from the central part of the left ventricle, and I'm going to tilt it up such that the beam is now tilting towards the, superior aspect, like towards the patient's head, right? And then it starts to intersect things like the mitral valve, right here, and the aortic outflow tract here, and the left atrium here. So we're just over time just tilting up. You can imagine while you're doing that, these things are beating along, and you're seeing what's going on, right? This plot down here is over many heartbeats. So this is an EKG down here, these blue lines. So each one of these blue lines marks a new heartbeat, okay? And what I showed you on the last slide, a B mode image is one of these vertical lines here. So I'm just holding the transducer, looking at that B mode change over time, and you can see what that looks like. And this one, the It's the central line of this thing here. Okay, so forget about all this stuff out here. We're just going to measure this central line. And you can see this part here, that feature is when this piece of tissue moves in. Okay, so this is moving in. This feature down here, okay, is when this piece of tissue moves in this way. And so you can see cardiac contraction over one cord through the left ventricle with ridiculous time resolution here, right? So if you wanted to know the acceleration or the jerk or higher order derivatives of the motion of this piece of tissue, you would look at this curve, right? And so we do that for a couple of beats, right? So we've got 2 heartbeats here. It's coming in, filling with blood, coming in. Now we're moving into a slightly different location, more towards the top of the heart as we move this way. And then these features come in, and these are valves, right, that have come into the field of view here, right? So that's kind of cool. This dashed line here represents pretty well this line across here, right across there, right, to position yourself up and down on that. Okay, any questions about that? That's called M mode imaging. It's done not only in echo, it can be done in MRI and not so much in CT, but you could do it. But in MRI, you can excite a cylindrical volume of tissue, and it doesn't take long to image to put a frequency encoding pulse across that line and watch it move in real time, right? So M mode MRI is something we did it a lot in aortas, for example. We would put a cylindrical excitation down the descending aorta, right? And then measure the phase shift of the blood as it flows down the aorta. And you didn't have to do any spatial encoding because you isolated your signal to that blood in the aorta, and then you got a phase map along that line, and it was very, very fast, right? And so you can measure stuff like the acceleration of the blood and whatnot. We thought we could predict when a person was more likely to have a rupture in their aorta, right? Because what happens sometimes is people's aortas start to expand, they dilate, and you see it on their CT. It's easy to see, obviously, and on their MR, but the question is, like, when's that thing gonna rupture? When it ruptures, it's a big deal, right? Because you bleed out. So you kind of want to go in and put a stent in there. But you don't really want to do that until you have to. It's this balance, right? So images like that, very valuable. And ultrasound is used a lot in stuff like that. So just this slide just reviews, I think we've talked about this enough, basically the phasing of the oscillation of these individual elements and sectors on the transducer can change your focal position and depth, right? And so we change our focal position over here, we basically have a beam that's going sideways, right? And then we change the focal position to here and here, and we can sweep back and forth just by doing phase shifts on the individual elements. Right. This was a picture from Princeton Links, and I'm fairly confident that Dr. Prince, who I know quite well, got this from a reputable source. So here's what a pulse looks like in time for a resonance transducer. So this is if you ping a piezoelectric crystal that actually has a resonant frequency, right? So when you ping that and see what comes out of it, this is the type of waveform that comes out of it, okay? And you can see there's a rapid increase to a maximum amplitude and then a kind of a decay envelope here. So the whole thing is only about a microsecond long, right? So these decays can be modified by putting different materials against the crystal. So just like you would change the resonant frequency of the springs in your car by putting a shock absorber on it, right? You want to dampen, you don't want your car bouncing up and down. You basically want the wheel to go bloop over the pothole and then just rapidly decay, right? And so you can put these dampers in. Same thing with this, you want to dampen out this ringing. And if you can make a broadband transducer by increasing this damping such that you have to drive it, right? So that basically whatever voltage pulse you put in, you're going to drive that crystal to do it. Okay. There's questions over there. Let me take a look for it. Sorry. Sorry. Would the focal point of focused ultrasound show up as an object on conventional ultrasound? Well, that's a deep question. Anyway, so do I have two ultrasound systems working simultaneously or one here? Because you could imagine like having a focused, like a therapeutic focused ultrasound system producing a vibration and then actually imaging that in real time with another system. But I don't know. I don't know the question. The answer is I don't know, depending on what we're actually doing there. Oh, you sweep through the whole field of view. I guess this was a while ago. We had a slide on that. So basically you change the phase array such that the direction of the beam changes. One imager and one focused ultrasound device. Yeah, I don't know. That's a great question. You would imagine that when the focused ultrasound device is causing a large amplitude vibration at, in a 1 centimeter sphere or something like that, that would show up on the other ultrasound device as something, right? Whether or not it would be, if you image, say, outside the frequency range of the therapeutic device, such that it was just a change in the impedance at, say, the diagnostic frequency. So say we had the therapeutic device at 1 megahertz and the diagnostic one at 3 megahertz. So they're outside each other's bandwidth. You would imagine you would see something. I don't know if that's true. That's something to look up. You could probably Google that and figure that out. Okay, so here, this is, the reason the thing's so big, although you can get them on catheters, so they don't have to be this big, but you have this acoustic backing on the backside of the crystal, excuse me. And then that is coupled tightly to a matching layer. And the matching layer has an acoustic impedance, which is the geometric mean of the acoustic impedance of the crystal and what you expect to see in the tissue. It's like a stepping point to get the energy out of the crystal into the tissue without having it all sort of reflect right off the surface. That didn't help anything. Okay. And this this slide describes it describes the time gain compensation. So if we have a substance And I have these boundaries here that basically have the same change in impedance. And so the amplitude of the reflection is the same, right? But as we go down into the sample for a couple of reasons. One is the heating up of the sample, and the other is just the geometry of the situation. When I have a point reflector here, it reflects out in basically as a spherical reflection, right? And I'm gonna sample a little spot on that spherical reflection. So there's a dramatic drop in the power of the stuff coming back, right? If, you know, think of a little bead at a meter here and I shoot a wave at it, when it reflects back, it's going to come back as basically a sphere, right? It doesn't focus that stuff back to me. It comes back. And so when I cut out my little, you know, receiver, it's receiving a very small amount of that. And that goes as actually the depth squared, right? That term. Which is also, you know, it's the same thing with like the brightness of a star. When you look at a star, and it's many light years away, it has made a spherical shell of photons coming out of it, and you are sampling that enormous spherical shell with a little tiny diameter of your eye, right? And you still see the darn photons. There's enough photons that you see them, and that thing's a long, long way away, right? And does anyone know what we could talk about hearing thresholds too, but for your eye, this always amazes me. Like when you see a star and it's coming in and out of perception, right? So sometimes you see it, sometimes you don't. Sometimes you have to look a little bit off to the side and you'll see the signal better. That is like 5 to 10 photons is what you're detecting. You know, so you are a really good photon detector, a photon bucket, right? So so anyway, you apply this time gain compensation, and this is a very sketchy curve. This thing is a log scale, okay? This curve here. And then after that, because all of these are the same transition, you would actually like them to have the same amplitude, right? You know, that's because it's characteristic of the transition between those two materials. Get it even, and then you demodulate the signal down to these, and that produces your A line, which is what we're going to use to make that B scan, which is what goes into the M mode. And then eventually the 2D image. Okay. Now, there's a interesting phenomenon that occurs with sound going through a material. And let's see how I could put it. Where should I put this thing? I put it here. Does anyone know how to get rid of that thing? Because there is no way, right? I used it for 2 years and I can't get rid of it. So here's a sine wave that starts out from our transducer. We've created this vibration, and say it's moving through the liver, right? And it's, you know, pressure versus time. But it turns out that the high pressure part of this phenomenon travels faster than the lower pressure parts, okay? And what happens then is the wave over time essentially it almost looks like it's a braking wave, right? The peak basically pushes forward, right, over the lower pressure parts. Yeah?
So related to quick mortgage. Yes.
Is that right?
Yeah. High floating.
Here? This? Oh man, 2 years of pain. Solved. Thank you. Okay. Oh, that's great. Wow, that makes my day, I gotta say. Okay. So anyway, this is a really cool phenomenon, right? So that the pressure wave traveling through the tissue actually changes its shape, right? It gets distorted by this factor that the high pressure stuff moves quicker than the lower pressure stuff. And so you eventually get more, as you go deeper and deeper and deeper, you eventually get more into as a sawtooth that is traveling through the material than a sine wave, right? And if you look at a sawtooth and you say, well, you know, what are the frequency components of a sawtooth, right? It has higher frequencies at specific overtones, right, than the primary. And so and this is called the, you know, the nonlinear interactions of tissue for this type of wave transmission. And so what gets reflected back, right? What you see at the transducer, because it's done a round trip through the tissue, and this type of distortion has had time to evolve. You see the primary component, which is obviously the primary frequency here, plus these harmonics, right? In order to create this shape. So it, you know, and initially it's probably discovered and people say, well, that's just an artifact. We're going to have to deal with this artifact. We have these extra components as opposed to our primary, which is obviously the one we want. And, you know, in imaging, it's always the same. One person's artifact is another person's technique. If you have artifacts in your picture, you should always try and figure out how to make that signal useful, right? How to isolate something with that signal, or, you know, produce an image that is only that signal, something like that. That's a classic one, right? Because an artifact is not random noise, right? An artifact is a process. It creates a signal you actually don't want right now, but it's an interfering process, but it was made by some underlying process, right? So the other interesting thing about where that signal comes from, so when you come back and you see this distorted wave, you ask, well, where in the sample is it coming from? It is coming more centrally in your beam than in the lateral parts of the beam, right? And because the pressure is highest here in the central part. And so as you go deeper into the object, the signal that is comprising that distorted part of the wave is becoming a more central part of your reflected beam, right? And so this is going to help us in two ways, right? It's going to help us focus the beam at depth, and it's going to help the slice thickness become thinner at depth, right? If we just look at this signal, right, we know it's coming from this part of the sample and not out here. And so in both, you know, the basically lateral resolution and the slice direction, the whole thing's going to collapse down and be higher resolution. Right? This is called harmonic imaging. And so here's one example of standard imaging in which you only process the fundamental frequency and look at the signal from the fundamental frequency. And then this little bright thing here, that's why I turn off the light. You can't see it. Oh, well, you know, you can't see it there, but you can there. That's good. So the contrast here for this hemangioma, which is a cluster of vessels in the liver, is much lower just looking at the primary frequency of the ultrasound versus looking at those harmonics that are, you know, twice the frequency. Right? And it's fairly easy to filter your signal such all you see is the twice the frequency, right? That's pretty big bandwidth. You just take the primary right out of the picture. Here's an example from what was this? Oh, this is from that paper. Remember I said I put a paper on tissue harmonic imaging, the review paper. This is it here, and in the notes, you can just look it up yourself, but there's also a copy on Canvas. And then this is out of Bushberg. This is an example of essentially the primary image at depth, and you can see it's imaging a kidney. So the transducer is way up here at depth versus the harmonic imaging at depth. And so this is just looking at that higher harmonic component of the signal, right? And you get essentially higher resolution and fewer off-axis blurring effects. Okay, so any questions about that stuff? No? Okay, good. So now we'll take a look at this Doppler effect. It's used a ton in ultrasound. It's not just in cardiac, but also in peripheral artery imaging, imaging in the carotids, and anywhere where you have flow and you want to see what the peak flow is or such. And it's, the Doppler effect is well known to all of us, right? In that an ambulance, as it's coming in, it has a siren, and it has a primary fundamental frequency of the siren. And as it's coming towards you, right, the sound waves are being, or the peaks are being compressed, right, by the fact that it has velocity towards you. And so as you hear that sound wave, it sounds like a higher frequency. And then when it passes and goes by, the peaks in the sound wave get stretched because it has velocity going that way, and you hear the sound go down. That's classic Doppler. So you can do that with, for example, blood or small spheres that you inject into the blood in the body, in that if I have something that's emitting because it's reflected sound, so now it's an emitter and it's reflecting sound at a specific frequency, if it's moving while it's doing that towards you, then the sound you hear gets, pushed up in frequency. And you just measure that frequency difference, and you can measure the speed of the thing that's transmitting that sound. Right? In Doppler, where we do pulsed mode Doppler, there's a factor of 2 involved for this jump in the frequency of the sound, and that is because if it was just, if we didn't reflect anything, if it was just an emitter and it was coming at us, we'd see a shift in frequency proportional to its velocity. That's actually not what happened. We transmitted sound at it, right? And so when it received the sound, it also got shifted up in frequency, right? And so it shifts the frequency up as it's a receiver, right? And then it retransmits, and it goes up again in frequency. Right? So that explanation is done algebraically, if you'd like to see the algebra in Princeton Links, right? It's like on one page, where he models the emitter, i.e. the boundary, the reflector that we're looking at, as first just a reflector that is transmitting sound, and then you ask, well, what frequency does it see the transmitted pulse? And you combine those two, and you figure out this equation here. That's where the factor of 2 comes, right? Because when you look at the equation just on its own, you go, oh yeah, I believe that. Where the hell does that factor of 2 come from? It's like, what's that doing there? So you can imagine also, it depends whether or not your transmission and reflection are on the axis of the velocity, or are they off the axis of the velocity. Obviously, if they're 90 degrees to the velocity, you're not going to see anything, because it's not moving towards you or away from you in that direction. So at 90, this effect goes away. At 0 or 180, the effect is maximized. And at 0, you would see a shift up in frequency, and at 180 you would see shift down if the object's moving this way, right? So it's pretty simple. You can calculate what, you know, the dynamic range of your measurement has to be in order to measure these shifts in frequency. So here's an example where you have a transducer here, right? And we're, you know, so the beam is coming down this way, and that's a very nice geometry, and as is this, right? To measure velocity across the mitral valve and aortic valve. Right? Remember, velocity is coming toward the transducer here, they're yellow, and away from the transducer, they go into the blue. And here you can see there is red stuff, right? In this, you know, part of the left ventricle, which is still flowing this way, and this stuff is turned the corner and is flowing back, so it's like a swirl, right? And this stuff's getting pushed out the aorta. So at this part of the ECG, right, this is where the heart relaxes and the mitral valve opens up and blood flows in to the ventricle, right? And so it's coming towards the transducer in this, right? And we saw an example. Do I have the example? Oh no, I don't have the example here. Let's go back and look at the, I'm pretty sure I have them. There we go. Do we have a movie of this? Oh, here it is. Yeah, this is great. All right, so this is what ultrasound is really all about, is the fact you can do this dynamically in real time, watch it happen on the screen, you know, with the patient at their bedside. So somebody comes into the ER and they're lying in a bed and they're in big trouble and you don't know what's going on. You roll one of these machines up, they come with 4 wheels and you plug them into the wall, right? Or run it off the battery and you just roll it up to the bedside and doom, doom, doom. In 30 seconds, you're looking at something like this, right? And so it's tremendously powerful that way. And in this patient, right, we can see the blood is moving when the mitral valve opens, the blood is moving towards the transducer, but then when the ventricle is ejecting, we see this blue jet. So that's got the wrong sign, right? It's going the wrong way. And you know, this could be the reason why this patient has hit upon hard times. Might be something else though. But what happens here is because a certain fraction of the blood, sometimes upwards of 50% or more of the blood, is going back into the left atrium. It's not going out the aorta. So you need to beat your heart, you know, your heart has to beat twice as many times just to keep your cardiac output, right? And so you get exhausted, right? And so basically your heart just tries and tries and tries to keep up, because if you don't have the right cardiac output, you are just going to sit in a chair and do nothing, right? You're going to be totally exhausted. And so that's it. Sometimes it just wears the heart out. It just, you know, eventually fails. Okay. Okay. So we're just going to look at a couple of artifacts. Artifacts are often a great way to really understand how something works. And look at this. I'm just going to turn this off. Okay. Okay. So if we have a boundary between 2 tissues, right, we get an echo from that boundary. If that boundary is at an angle, so we're going to get refraction at that boundary. And so the beam will actually bend with respect to the boundary, right? And so distal to that boundary, it may cause, you know, objects that are beyond the boundary to be mapped to the wrong location, right? So if we look, here's, you know, we've got 3 objects and a boundary in our field of view. When I take this orientation, right, which is the straight down orientation, and I ask, well, what does the echo look like beyond the boundary? Well, I don't get an echo from beyond the boundary. It doesn't look like there's anything there, right? And then when I rotate my beam such that I'm off on this line, right, I now get an echo from this spot, and it's going to erroneously believe it came from here, right? So it's shifted it over, right? So when I make the 2D picture, this object, which actually is here, shows up over here. Okay. And so that kind of distortion with all these angular boundaries can cause, you know, issues. There's a whole bunch of really good artifacts in this book chapter. We're just going to do a couple here. We can, if you have some time, we can go into the chapter and look.
What are the interaction numbers?
Say that again, I'm sorry.
The interaction numbers, like that's the one of the area of the, or you have like
I don't understand the question.
so
Sorry.
how the angle of refraction
Yeah.
changes based on the angle.
Oh, how does it change? Oh, that's a great question. Well, so
It's
the,
like optics, it goes like
I think it's just,
the,
yeah, I think it's like optics, but they, you know, it depend on the different Z values of the tissue, like what that boundary would be, and then it'd be absolute reflection. Yeah. Yeah. Yeah, I think so. So, yeah. And then some pretty simple stuff is if you have a very low attenuation here, right, then beyond it, you get a negative shadow, right? You get something that is amplified the amount of, like it maps the attenuation across this whole field here. And then if you get something that has a lot of attenuation, it basically just casts a shadow. And I would say this is probably the most common thing that gets in your way when you're looking at ultrasound images. There's something there that's casting a shadow that you have to try and work around and get around it. But because it's real time and you have the thing in your hand, a good tech, you know, sees an artifact like this and doesn't keep that picture. They just keep moving and find a picture that can get around that artifact. This is pretty cool. So if you have a really sharp, high impedance change here, such as you get a really strong echo, what can happen is that echo can hit the transducer, and then the transducer echoes it back, right? And so it basically bounces between the transducer and that surface multiple times. And each time it just thinks it comes from that much deeper, right, of the primary position than it was, because they're just like, here's my first echo, and then there's a second, third, fourth, fifth, and they just go down. And then that causes an artifact that looks like this, which it's a comet tail artifact, some people call that. And then here, where you have a large change in Z value, oh no, actually a large change in speed of sound, not Z value. your assumption is that the speed of sound is constant along here, but if there's a big chunk that has quite a different speed of sound, it will just shift everything in space because the times will shift, right? And so distal to say a big, lipoma or something like that, you'll get a change in the boundary will just shift backwards, right? So that's the speed artifact. Oh, as promised, here's an example. This is a very technical paper. I think if it's not in the supplementary stuff, I'll put it in there. But it's basically how do you measure, the contrast to noise as a function of depth for a specific transducer, and this is it's a nice paper of just how they set up the phantom, where they put the transducer. You try and make all these controlled measurements, and you can see the signal to noise or the contrast to noise between these spheres, the reflective spheres. I guess they look like air spheres. What are they? I've seen all spheres. I don't know what they're made of. Let me say. Okay. But as you go to, so here we are in depth in millimeters. So we're obviously working at high frequency, high resolution ultrasound, right? Because this is 1 centimeter, this whole thing, right? So this is probably a transducer that you would put on something to make a very high resolution picture. We have a frequency. Now the reason I picked this graph is because here is the contrast to noise of the object as a function of depth. And so, depending on the frequency, this depth would change. But it's quite obviously there's a focal point where you're getting this really good contrast to noise, a lot of echo per unit noise. And then as you move away from that, it rapidly decays away, right? So down here, you're, not the actual echo amplitude is decreasing pretty rapidly as we're going deeper into the sample. So, that's how you would do it for any transducer that you've got in your hand. You would make some phantom and put echogenetic stuff in it and measure these curves to optimize the phantom. Okay, I think we already looked at that. Okay, so that's all I got for today. In terms of the projects and the presentations, I did get a bunch of emails that I'm going to go through today and give you the thumbs up or whatever, so that by the end of today you should see those. We'll work on if anyone wants to give a presentation next Thursday, so it's a week from today. You can volunteer yourself, and so the first two people to first two groups that volunteer will get a little bonus because it seems a little short, right? So if you're ready to go and you want that bonus, that's great. If we don't do it Thursday, that's fine too. But that probably means we go into presentations during what would be the exam time, which is that first week in June, because I think our classes stop on the 2nd or something like that, and then we would, in the next week's exam week, we could do some presentations in there too. Okay, but it would be great to get them done before that. Okay. All right. Cool.